Assalamu alaikum. I am Naman Khan from the Department of Electrical Engineering, PIAS, and today I will be going to present our work on the control of a high voltage DC modulator of an industrial magnetron on the behalf of all the authors of the paper. So before going into the detail of this work, here is a quick overview of what we will be covering in this presentation. First, we have the background and introduction to the problem. Then we will discuss about some of the issues that we have tried to eliminate in this research, and then its simulation results have been presented. And finally, some concluding remarks will be presented along with a future work direction. Pakistan Tokamak Plasma Research Institute is focusing on the development of its own tokamak devices. And they have already worked on a 1 kilowatt and 3 kilowatt magnetron systems, and now they are working with a 10 kilowatt magnetron. These magnetrons and tokamak devices are required to study the controlled fusion and the plasma generation related problems. This work is a collaborative work between PIAS and PTPRI, and the purpose of this work and the major goal of this project is to design and develop and come up with an indigenous design for these high voltage DC power supply for the anode of the magnetron. It is necessary to come up with an indigenous design for these kind of power supplies because the suppliers are not willing to deliver such supplies to Pakistan, and additionally, the cost will be very much. Here we have some requirements and specification of the anode power supply. Here we have the preheating phase in which only a high current power supply will be working, and the anode power supply will not be, its output voltage will be kept at 0 volt. We are only working on the design and development of the anode power supply required for this magnetron operation. And it requires a two-step soft start, which means that after the preheating phase, it will be the anode power supply, it will be switched at 6.8 kilovolt, and it will be kept over here for some time. After that, we will switch on to the next stage of 8.8 kilovolt. That is the steady state operation of this magnetron. And during this, the first step, you can see we have no current flowing through the anode of the magnetron. And as soon as we will switch on to the second step, a current will start to flow from the magnetron. So it is very necessary to follow this type of waveform, and it should have such type of transient response. The characteristics of these anode power supply are its nominal voltage is 8.8 kilovolt. Allowable range is in plus minus 200 volt with respect to the nominal voltage. Average anode current is 1.8 ampere. Peak is 2.2 kilovolt. Its input power should be 16 kilowatt. And standing wave ratio is 1.5, and anode core temperature maintained to be at 130 degree centigrade. In addition to all these requirements, the power supply has to follow the waveform characteristics shown in this slide. In our previous work, we had designed an unregulated high voltage power supply that was capable of meeting the power requirements of such power supply. And this series resonant converter based design was selected as a suitable topology for the fabrication of anode power supply due to its phenomenon of soft switching, fewer switching losses due to the switching being held at zero crossing, due to low electromagnetic interference, and due to its inherent safety features during the short circuit. Here we have a schematic circuit diagram of the topology. Here we will have a three-phase supply. It will be first rectified using a 6-pulse rectifier. Then some filtering will be done at input side so that a pure DC is fed into this half bridge inverter. And then we have our resonant tank. After flowing through this, the current will be sinusoidal, and the zero switching can be now held. And then we have a high frequency step up transformer, on the base of which we will be stepping up the voltage to the required level. And then again, we have a single phase full bridge rectifier at output. And once again, it will be filtered, and the pure DC will be fed to the magnetron load. We have come up with a modular design where we will be developing 3 modules of 3.4 kilovolt, and they will be cascaded together in order to meet the overall voltage requirements of the output voltage. Here we have shown the phenomena of zero current switching. This is the current flowing from the resonant converter, and this is our voltage waveform. You can see that the switching is being held at zero crossing. This is done. This topology was specially preferred due to this particular feature because this is a power-intensive application. The current at the primary side of the transformer will be very high, and non-zero switching, or you can say hard switching, could not be tolerated. The power surge losing would have been very much increased. Therefore, we remain to this topology. When the circuit shown in the previous slide, that was simulated, this type of response we obtained at output. This was the first step of 6.8 kilovolt, and then after some time, we switched on to the full scale power over here. Here we have a slightly higher voltage than 8.8 kilovolt because we implemented 3 modules of 3.4 kilovolt. It was done so that if we have some undershoots in the input power supply, input 3-phase source, so that still our power supply can be capable of meeting these requirements. But here we have this type of transient response that is not that is clearly not acceptable for magnetron, being very sensitive load. Therefore, it was a need so that we remove such transient behavior from our output. Otherwise, our magnetron will be damaged immediately. It was due to, on investigation, we come to know that this was due to the some surge current drawn by the filters at the input side. So there was a need to, there could be 2 methods to eliminate that. One, the pre-charging of the capacitors at the input and at output, and secondly, by applying control. When the input filters, they were charged up to their maximum value of 540 volt. In that case, we can see that the surges have reduced to a very respectable amount, but still such type of response will not be acceptable for the magnetron, being very sensitive load. This is from the this surge is still violating that limit of plus minus 200 volt. Even though this is for very short time, but it will damage the magnetron. So we came up with a solution that we have to implement a controller. And in order to implement a controller, we have selected a frequency based on the base of frequency changing. We want to change the output voltage of this resonant converter based supply. The transfer function for a series LLC resonant converter is given by this. Here Q is the quality factor and capital F is the normalized frequency. Where if the quality factor of the system increases, this notch of this filter, it increases. And we see that by changing the resonance frequency, by deviating from the resonance frequency, we can decrease, we can control the output power. And quality factor is given by this, where R is the output load, and LR and CR are the resonant tank values. Based on the LR and CR selected for the magnetron power supply, the Q came out to be 0.54, and such type of response was uh, seen, which is pretty much similar with this one. Q is equal to 0.5. So still, the selectivity of such type of a resonant converter is slightly less, but it is acceptable, and we can, by varying the frequency, we can control the output power. So on the base of this theory, we came up with this closed control loop on all modules. By changing the frequency of the gating signal of the inverter, we can control the output power. We will have a reference signal, and the output signal, their difference will produce some error signal that will be passed through the controller, and that controller will generate a signal, and it will be fed to a voltage controlled oscillator. Based on the magnitude of this output voltage generated by this controller, VCO will either produce a frequency of greater than resonance frequency or less than resonance frequency, and that will be fed uh, to these converters, and output voltage will be. Here is the detailed structure of the control that we want to implement. Here is, in this first part, we are comparing the output voltage with the input reference, where we have two blocks of 6,800 and 2,000. For the first step of 6.8 kilovolt, only this stage will be working, and for the next stage, where the steady state operation, when our output voltage will be at 8.8 kilovolt, both of these will be generating the reference of 8.8 kilovolt that will be compared with the output signal, and an error signal will be generated that will be limited by this saturator, and that signal will be then passed to this PI control, and on the base of that, it is now multiplied with the gain, and it's and this bias value will be added with the free running frequency of this power supply of 22,500. At 22,500 volt, the output voltage of our this three modules will be 8.8 kilovolt. So if based on the value of what the bias this thing will be producing, and the sum of this free running frequency, either our frequency will be increasing or decreasing. We have put a minimum value of 20,000 and the maximum of 40,000 here. So it means that we are trying to control the output voltage by staying in the frequency greater than the resonance frequency, which was 20,000. And this, based on this frequency, it will generate a voltage level, and that voltage level will be fed to the VCO, and that VCO will be generating, will be providing getting signal to the half bridge modules, and based on the frequency of those getting signals, we will be controlling our output voltage. So here is a demo of how the VCO will be working. Here we have applied a ramp input. As the magnitude of this voltage will be increasing, the frequency of this VCO output is increased. So based on whether the magnitude of the input to the VCO has increased or decreased, our frequency will either increase or decrease, and we can control the output voltage. So these were our required characteristics, and these are the achieved characteristics by implementing the PI control. So not only now we have obtained the output voltage levels of 6.8 kilovolt and 8.8 kilovolt, but also we have achieved that particular transient response. Here is the effect of variation of the slope of this waveform. If we keep on increasing the slope of this waveform, the rise time of this waveform, it will increases. But if it is increased beyond a certain value, some overshoots start to appear in output again. So here, based on this simulation graph, we will select some such a value where the rise time is also minimum and there are no overshoots in the output. Here, at different by varying the input voltage higher and less than the rated value, the performance of this PI controller was tested, and the response was very stable up to 20% decrement, and only variation started to appear when the output voltage was varied more than the 25%. Uh, whereas by increasing the input voltage, we were capable of tracking the required characteristics even up to 20%. Then the controller was tested by decreasing the load, load, and you can see that some ripples start to appear when the output resistance is varied beyond 2500 ohms. The nominal load resistance of this magnetron was 5500. And similarly, when they were increased beyond a certain value, then there certain overshoots started to appear. So the conclusion, so basically we have implemented the BA control, and the output voltage control has been achieved. We have developed a 3.4 kilovolt module already in our lab, and we will be testing it. First of all, we will be testing that one module with a controller, and based on the results that we will achieve, we will implement we will be developing two more modules, and we will implement the cumulative controller on all these three modules, and we will hopefully achieve that in near future. Thank you very much.